Okay, so far we spoke about the Peano axioms. And what that list of axioms does is to define the natural numbers in some abstract fashion without worrying about what those numbers mean and so on. It just tells us some properties that this set satisfies. So, let us try and use those axioms to prove some what would be familiar statements about our usual way of thinking about the natural numbers. So, here is one. Every element of the natural numbers, we talked about the successor. So, given any element of n, there was this other element of n called the successor of n. That is, we think of it as sort of the next natural number. Now, so this was the successor. Now, we can likewise define something called the predecessor or the previous natural number. So, how do we formally define this? So, let me say definition. If x plus, if x is a natural number such that x plus equals n, then we call x as a predecessor of the natural number n. Okay, so, x here is again an element of this set n here. Now, so let's see what we can prove about predecessors just starting from the axioms. So, the first thing here is that if predecessors exist, then they are unique. Okay, so, predecessors of n, there can't be two different predecessors. So, the predecessor is unique. Okay, so, what do we mean by that? So, what should we prove? So, here is what we want to prove, that suppose if two different numbers, if x and y are two numbers such that both x and y are predecessors of n, that is x plus and y plus are both equal to n, then we want to prove that x and y are the same. In other words, there is only a unique predecessor. So, let us prove this. So, let us again start with this is just a direct axiom. So, proof of this is just recall there was an axiom which said that, so this is one of the Peano axioms. One of the axioms said that said exactly this: if x plus and y plus are both the same, then x must equal to y. Okay. So, this was one of the properties of the successor function. Okay. So, I should say one of the Peano axioms said this. Okay. So, that is our proof, that if the successors of x and y are both equal to n, then x must equal to y. This just comes from one of the Peano axioms directly. Okay. Now, here is the first interesting thing we will prove about this, that suppose we go to, so let us look at elements which have predecessors. So, here is a little statement, so which we call a proposition. Okay. So, it says the following, that every element of n has a predecessor not quite every element of n except for that special element which we called 1, except for 1 has a predecessor. Okay, so, this is of course intuitively clear to us because of the way we think about natural numbers. We know that every number has a previous number except for the number 1, which of course does not have a previous natural number. But again, the thing here is we want to prove these sorts of statements just using the axioms. So, that is the key point here. Okay, let us prove this, and again remember we have to use only the axioms to prove this. So, it requires some amount of creativity to construct a proof of statements like this only using the axioms. So, what we will do is to use the principle of mathematical induction, that is one of the axioms. So, what we will do to prove this statement, so let us do the following, let us define a set called P to be those elements of n which have a predecessor. Okay, take those natural numbers such that n has a predecessor. Okay, and let me just do something slightly extra here. I will also attach the element 1. Okay, so what I have done here is taken the union of these two sets. So recall the first set here, the numbers n which have a predecessor, 1 does not belong to that set. Okay, so that was one of the axioms of let us do it in 2 steps maybe. So let me first define P, which is those numbers which have a predecessor. Then recall that one of the Peano axioms, by one of the axioms, we know that 1 cannot be an element of P because 1 does not have a predecessor. Okay, so what we will do is we will throw that also in. So let us define a larger set, we will call it P hat to be P along with this extra element 1. Okay, so I have defined this new set, and now what I want to prove is that P hat is the entire set of natural numbers. So want to prove that P hat is everything. Okay, that is exactly the same as what we need to prove in the proposition. Every element other than 1 has a predecessor is the same as saying the set P hat is the entire set of natural numbers. Okay. So let us prove this. We will do this by the principle of mathematical induction. So what does that require? So that axiom says, let us use this principle of okay. So we will use this. So what does it involve? So we will first show that we need to show that 1 belongs to this set. Okay. So that in this case is easy because we sort of specifically threw that in. So 1 is an element by choice. Now so that is okay, we have checked that. Now the second thing we need to check is that if some element n belongs to this set, then so does the successor of n. Okay. So now observe, then we need to check whether n plus also belongs to n. Okay. Now why is this true? So is this true? This is what we need to check. Now this is true because of the following sort of simple reason. N belongs to P hat means that n is either the number 1 or it is an element which has a predecessor, but we do not even need that to show that n plus belongs to P hat is what I need to check here. Now let us check that n plus belongs to P hat for any element n of n. Well, what does it mean? N plus, it's let's call this our element say y, let's call y as n plus. We need to show that y has a predecessor. Okay, but what is the predecessor of y? Well, that is exactly n. So observe, if I define y as n plus, then sort of by definition it is sort of very silly in some sense, then n is the predecessor of y, just by definition. So that is what being a predecessor means. Okay, so in some sense there is very little to prove here, it is more or less just the definition. Okay, so this is also true. In fact, to prove this I did not even need my hypotheses, I did not even need to know that n belongs to P hat. Any element of the form n plus is automatically has a predecessor, which is the number n itself. Okay, so we have checked the 2 properties that we require for the principle of mathematical induction. So by the principle of mathematical induction, which is again one of the axioms, we know that P hat must coincide with the entire set of natural numbers. Okay, and that is exactly what we require to prove. So that is the end of the proof. So we denote the end of the proof by this little box here. So proved. So maybe I should write that as. Okay, so this is a little example of a statement that one can prove, which is sort of maybe obvious given our usual way of thinking about the natural numbers, but Nevertheless, it is a statement that we can prove in this manner purely starting from the axioms. Okay. Now, here is the other important statement we will now prove. And this is this is at the heart of how we define the natural numbers. The natural numbers, so let me just do this on the side. Recall for us what is now the natural numbers. It is a set which satisfies a set of axioms, okay, set satisfying some collection of axioms, okay, which ones? The Peano axioms. Okay. Now, what we would like to know, so what we are saying right now is that the natural numbers is this guy, it is this set which satisfies these axioms. But what if there were another set which also satisfied these axioms? Okay. So, that is something we have to worry about. What if we have some exotic set which also satisfies the Peano axioms and which does not turn out to be like our usual idea of natural numbers, right. So, this was the whole point of wanting to define the natural numbers in terms of axioms. So, we want to know the following, that any set which satisfies these axioms must really be the same as n in some sense, okay. And being the same as is, we just talked about, so you have seen this before, what when we would like to think of two sets as being the same, that there should be a bijection between them, a one-to-one onto map between these two sets. So, let us formulate this statement. So, if X is a set which satisfies the Peano axioms, okay, what does that mean? I will just say it briefly here. Satisfying the axioms firstly means to each x in X, I should be able to define a successor function. So, given x in X, there should be an element called x plus in X, the successor of X, such that it satisfies a bunch of properties, okay. And then there is also a special element called 1, but just so as not to confuse with the usual 1 in the natural numbers, I will just put an x under the 1. Okay, so, there should be two things, there should be a successor function for each element of x and there should be a special element called 1, and then with these there is a bunch of axioms, right. So, plus then we write down the various Peano axioms. Okay, so, I am not going to write the axioms down again, just remember that these two things are given, that there is the element 1 and then there is the successor function. Okay, so, if X is a set satisfying the Peano axioms, then we claim that X is in some sense the same as n, okay. Then there is a bijection, there exists a bijection, let us call it f, from the usual our way of thinking about the natural numbers to the set X. There is a bijection from n to X further such that this bijection sends the number 1 of n to this special element 1 sub x of X, and the successor function on the left hand side. So, if we take the successor of n, that maps under this function f to the successor of f n, okay. So, this should be true for all n n. So, this is the claim here, that this is what it means to say that the set X is in some sense the same as the set n. There should be a bijection, but a bijection which also respects these two additional structures that are given, the special element 1 and the successor function. Okay, again we would like to prove this purely starting from what we know about the Peano axioms, just from the axioms themselves. So, let us do this. So, here is the proof. We first have to define the function. So, define f as follows. We already know what we want to do, some things at least. We would like to map 1 to 1 So, let us send 1 to 1 and let us now define f by induction. Okay. So, this is the first thing we do. This is a recursive definition or an inductive definition, assuming we know the value of f of n, assuming f of n has been defined, we will define f of n plus the next element, right. How do you define f on the successor of n? Well, this is just take f of n, which you have already defined, and then take its successor. Okay. So, the successor on the right hand side is an element of x. So, recall this is f of n is an element of x, and so f of n successor is also an element of x. So, these two conditions define f on every element of the natural numbers, right, just by the principle of mathematical induction. It says if you have if you have any property that is true for 1 and then it's once assuming it is true for n, it is true for n plus 1, then it holds for all natural numbers. So, here the property we are looking at is whether f is defined for a natural number. So, f is defined for 1, that is true, and if assuming f is defined for n, we have said how to define it for n plus. Therefore, by the principle of mathematical induction, this definition defines f uniquely on every natural number. Okay, so, the definition has been given. Now, what we would like to do is, so I mean the definition actually satisfies the two properties that are there in the proposition. What we now only need to do is to show that it is a bijection. So, want to show that f is a bijection. Okay, and bijection means two things. It's got to be an injection and a surjection. In other words, it should be a 1 to 1 function and it should be an onto function. So, those are the two properties that a bijection needs to satisfy. So, let us prove each of them in turn. So, let us first show that it is an onto function. Okay. In other words, every element of x is there in the image of this function. Okay. So, first let us show ontoness. So, to show ontoness, let us look at the image of f. So, what is image or range of this function? So, consider the image, which by definition is just, so I will say consider the image, which is just all elements which can be realized as f of n, right. This is sometimes called the range of the function f. Okay, here is a set of elements of the form f of n, this is some subset of x. Now, the claim is that this image is the entire subset x. Okay. Now, how are we going to prove that? So, claim this is the whole set, that is what ontoness means. So, image of f is the whole set x, and to prove this we will use the principle of mathematical induction again. Okay. So, what does that mean? So, we will use induction. Okay, what do we need to do? We need to show two things. We need to show that 1 belongs to this set, 1 belongs to the image. Okay, why is that true? Because that is how we define f of 1. Okay, so, this is true because 1 is nothing but f evaluated at the natural number 1. The second property is that whenever something belongs, so if x belongs to the image, then its successor should also belong, then x plus also belongs. So, this is the second property we need. Now, let us see why this is true. So, let us start with the given assumption. We know that x is in the image of f. So, what does this mean? This means that x can be written as f evaluated at some natural number n, okay, for some natural number n. Now, we need to ask whether x plus can also be written as f of some natural number. Okay, so, I want to know whether I can write x also, x plus also in the same way as f of something. Okay. Now, we do know something, we know how f was defined. So, let us go back to the definition here. So, f was defined like this, f of n plus is f n plus. So, what does that mean here? So, let us just apply it to this element here. to n, then observe that if x plus is f of n, then so x plus is nothing but f n ka plus, that is nothing but f of n plus, this is just by the definition of f. Okay. So, now we are done. So, because now what this means is that x plus has also been realized as f of something. So, therefore, x plus also belongs to the image. So, what this means is that we have established the two properties required for the principle of mathematical induction, and so by the principle of mathematical induction, we conclude that this subset image of f is actually the whole set x. Okay. So, that is the end of the proof of ontoness. So, this proves ontoness of this function f. Okay. So, we have used the principle of mathematical induction to show that this function is onto, but that is only one half of showing it is a bijection. So, sort of in a similar spirit, and maybe that is something to look at during the exercises and so on. So, a similar proof, again using mathematical induction, also establishes that f is 1 1, okay, and that shows that it is a bijection. Okay. So, this is just to give you a sense of the kinds of proofs that one has to construct just using the axioms alone. Okay. So, we are not allowing ourselves the use of our familiar ideas of what a number is and so on.